My name is Zach Montgomerie, and I'm a fifth year PhD student in the SPACMATS lab at Stanford University. So what our lab does is we use computational tools and theoretical modeling to better understand biopolymers, specifically DNA and chromatin. So what I'll share today is a project I've been working on in my PhD. So to begin, DNA can form non-canonical DNA structures. And what that means is in cells, normally we have bDNA, which is a right-handed form. However, under certain circumstances, we can get what's called left-handed DNA or zDNA. So where this can occur is during transcription, you have a RNA polymerase that's transcribing along the DNA strand. However, ahead of this DNA strand, you can get an overwinding or a positive supercoiling. And behind the DNA strand, you can get an underwinding or negative supercoiling. So from this negative supercoiling, this creates an environment where this left-handed form can appear. So using magnetic tweezer experiments, experimentalists can reveal these structural transitions. So if you have a DNA strand that's pulled under constant tension and you twist it positively, you can get what are called plectinines. And so these are coils that basically the strand is coiling over itself. However, if you twist it in the negative direction, you can get, instead of plectinines, you can get this transition over to left-handed DNA. So this appears in the extension diagram, and this is a measure of the overall extension over the length of the DNA molecule. And so this lowering extension is a sign of plectinine formation, whereas when you have this extended form where the length is not reducing, that's showing the transition to LDNA. So we use a model that incorporates two energy functions. The first energy is the conformational energy, and this includes the bending, twisting, tension, and torque contributions. And we demonstrate that in this model DNA. And we also include this 1D discrete model, which incorporates the energetics of the DNA switching from B to Z. So this includes an energy difference between B and L DNA, and as well as a junction energy cost of having B and L DNA together. So using our model, we can compare it with experimental extension data, and we see that it compares very well. So we had 4 experimental curves, which are shown with these dots: 4.4 piconewtons, 1.8 piconewtons, 0.8, and 0.3 piconewtons. And so we see that our theory can predict this extension very well, and we can also predict other characteristics and properties of the DNA.